Hi everyone, I'm Ludovic MELL, a third-year PhD student at University of Nantes, and I'm going to present to you my work, which is entitled Finite Element-Fidelity Parametrization of Kriging Metamodels for Structural Reliability Assessments. So the presentation today is going to be divided into 5 parts. The first two are literature on computation and the probability of failure and on reliability. On the third part, I will present to you the method we've developed and apply it in a fourth part. I will finally conclude in the fifth part of this presentation. So about the context, there might be variability or uncertainty on some parameters of the mechanical problem. These parameters may be, for example, the yield strength, sigma E, the Young modulus E, and F, the loading on the structure, that are gathered in a vector of random variable X. We may define a limit state function defining the failure or the safety of the structure as G equals R minus S, with R a resistance, for example, the yield strength of the material, and S a solicitation, for example, the von Mises stress at a given point of the structure. So this solicitation may be the output of a finite element code, in which the mesh size is basically the size of an element on the structure. So the objective is to compute PF, which is the probability that Gx is smaller than 0. So a bit about the literature on the computation of the probability of failure. There are two main families. The first one are the sampling methods, such as Monte Carlo estimation or importance sampling, for example. These may be costly when you are using a FEM code to evaluate the function G. Then you can also use an approximation method, which may be divided depending on the level of approximation. The first level would be the approximation of the mechanical response through stochastic finite element method, for example. This may be intrusive to the FEM code and do not allow to control approximation error. You may also use an approximation of the limit state functions through polynomial chaos, neural networks, or kriging, for example. This is usually used with the sampling method to compute the probability of failure, and it allows to control the approximation error in the case of kriging. You may also approximate the limit states through form, SORM, or through a classifier such as SVM. The approximation error is not controlled with form and SORM because there is no reason why the limit state should be linear or quadratic for any problem. And for SVM, it doesn't exploit the sign of J, and it does not exploit the value of the function G, which makes usually the approximation of the limit state function more powerful and more performant than SVM. So about adaptive kriging, the kriging metamodel G hat may write as G equals mu plus Z, where mu is a deterministic function and Z is a random function following a centered Gaussian distribution. The kernel function is chosen as Gaussian in this work, and you will obtain in the end a metamodel G hat and a standard deviation estimate sigma hat. A learning function can be used to select the next best point to be added to the metamodel. Let me explain. With a Fourier evaluation of G, you can build a metamodel and confidence interval within which the exact solution should lie. You have falsely classified point because of the limit state being not the exact one. So because you have high uncertainty on the value of the limit state, you can add a point close to the limit state and thus reduce uncertainty and falsely classified point. This is basically adaptive kriging for Monte Carlo simulation. I've written here the mu function that is used to select the next best point to add to the metamodel. So a first numerical example is the example of a crack place with a random crack length beta distributed between 1.6 and 4.25 meters and of shape parameters both equal to 2. The hypothesis we took is of small perturbations, linear elastic, homogeneous and isotropic material, plane strain, and the Griffiths criterion defines the failure of the structure if the crack propagates, so if the stress intensity factor K1 is greater than a resistance. So for R equals 14, you can see that depending on the mesh size H, you will obtain different value of the probability of failure. In fact, for H equals 0.5 meter, you obtain a probability of failure that is 0, while the exact probability of failure is 6.0 10 to the minus 3. This may be critical in the case of the design of the structure because you can think with a coarse mesh of 0.5 meter that your structure is actually safe, while in reality it's not the case. So depending on the value of the resistance, you can see that for example, for R equals 9, the probability of failure is fairly accurate with H equals 0.5 meter. So what it proves is that depending on the resistance, the appropriate mesh size to compute the probability of failure is different. So you cannot know a priori if your mesh size is good enough to compute your probability of failure. So what we want to do here is to compute PF with precision while controlling the discretization error. So about the formulation of the Msk Metamodel, so there are several a posteriori indicators of the error of discretization that write as a norm over the displacement field of the exact solution minus the one of the FEM field. It was used to estimate the probability of failure and bounds on the probability of failure in a paper we've already published. The problem is that a posteriori estimators are not always available in industrial FEM code. So we wanted to use a priori knowledge of the convergence of the finite element problem for linear quantity of interest. So it writes as following, with H being the mesh size and C and gamma being two parameters that are constant. So Taylor expansion near 0 would write as following. So what we proposed was to use metamodel G hat that is a function of the random variable, but also of H, the mesh size of the FEM problem, where the process G is now assumed to follow the equation that is written here. So now you have to estimate beta 0 and beta 1 during the construction of the metamodel. And the constant gamma needs to be computed before you compute this metamodel. So it is different from multi-fidelity co-kriging for a simple reason is that you are now able to get the limit state function and then the probability of failure for any mesh size that is continuously distributed, whereas in multi-fidelity co-kriging you will only get discrete levels of fidelity. First, you need to initialize your metamodel. And for that, we chose to bound the mesh size between hmin and 16 times hmin to bound coarse and thus precision on the probability of failures that we want to obtain at hmin. You need to distribute codes on different x and h for two reasons. One is to compute hyperparameters of kernel for x. So for that, we chose to distribute 12 points by light in hypercube sampling on hmax. And you need to compute gamma and estimate parameters and thus distribute calls on H. For that, we chose to find the point X, which is the point that we've evaluated on HMAC, which is the closest to 0, so to the limit state. At that point, we will call J of H for the different mesh sizes that is written here. With that, we can obtain the mesh size conversion rate with the formula written below. So if you want to choose a different ratio between the mesh sizes, you will obtain a different formula for gamma. And then in the end, we build a metamodel J hat with all observations. What I've plotted here is only the metamodel for H equals hmin, but you can obtain this limit state function for any value of H thanks to the metamodel we've developed. So then you need to define a learning strategy. Our learning strategy is to improve the metamodels at hmin in order to have a good precision of the probability of failure at this mesh size. So we need first to find the learning point xnext, which is found as the minimum of u at hmin over the Monte Carlo population. Then you need to find the mesh size hnext on which to evaluate this point. And we looked for hnext in the interval we've defined such that u at hmin equals 2 once this point is added to the metamodel. First, the metamodel is updated with a call at hmax for this point. And it allows to improve the metamodel at low cost. If it's sufficient, then there is no need to compute hnext. So let gh0 be the metamodel updated with xnext h0 of value g at xnext at 0. you need to find hnext such that u at hnext equals 2 at hmin, where u hnext is the function u from the metamodel gh0 updated with the point we've added. So what it allows this metamodel gh0 is to simulate the effect of a point added to the metamodel at mesh size h0 and see the effect at hmin. Building a metamodel g at h0 at each step of the optimization process makes it very costly. When you have computed hnext, then you just need to call g at hnext and update the metamodel. So we use two stopping criteria. The first one is on learning. So let the error of approximation be the relative error between the probability of failure without a metamodel and with a metamodel. There is methods in the literature to compute bounds on this error of approximation. It may serve as a learning criterion, and we chose it as the error of approximation at hmin being smaller than 1%. Then the coefficient of variation was chosen to be smaller than 10 to the minus 2. So about the numerical assessment test case, so we studied a gamma-shaped structure with the random variables being the modulus and the angle of the force applied on the upper right corner of the structure. So the parameters of the distribution are given in the two tables here, and the parameters of the hypothesis of the mechanical problem are given here. So I've also plotted a mesh at h equals 0.3 meters, and the function g is basically the a resistance that is a stress minus the mean stress in the square omega that is plotted on the left. So we studied 5 Monte Carlo population, but I will only show the results on 1 Monte Carlo population as it will be simpler to understand. So hmin was fixed to 0.01 meter. That fixes as well hmax to 0.16 meters. A multi-fidelity approach based on multi-fidelity co-kriging was run with 2 levels of fidelity, hmin and hmax. The results are given in the table here. On the right, I plotted the limit state with different mesh sizes and the call to the FEM code. You can see the results in the table here. What you can see is that the probability of failure at h equals 0.01 meter is similar with co-kriging and with our method. You can see as well that if you only consider TFEM and T-algorithm, the computational time is approximately the same between multi-fidelity co-kriging and our method. T-post represents the time spent computing the probability of failure at different mesh sizes. You can see on the left the probability of failure against mesh size using our method and different Monte Carlo population. You can see first that there is dispersion between population at h equal hmin and that the bounds do not include the probability of failure for every Monte Carlo population. This means that the approximation error estimator is not guaranteed. You can see as well that there is not a drastically higher dispersion at h equals 0.0001 meter. That proves that our extrapolation is probably fairly accurate. For further precision, a finer mesh could be chosen, and the enrichment strategy can be used with the metamodel already built earlier. So about the conclusion, a method to include the mesh size as a parameter of kriging to compute PF has been proposed. It shows approximately similar cost to a standard multi-fidelity approach. However, it allows to extrapolate the probability of failure to smaller mesh sizes and approximate PF with no discretization error. The method was tested on a second numerical example with 2 random variables. The hypothesis and the example is shown here. And you can see on the right the enrichment of the metamodel and of the limit states. A paper including this work has already been submitted. Thank you for your attention, and if you have any questions, feel free to ask them.